Hello everyone and welcome back to NTE. Let's look at another question from the prelim paper of Eastern Cape 2017. This question is now on the photoelectric effect. Quite a challenging question, not really question but section, because they can test it in a lot of different ways. So my only suggestion for this section is to really just jump into those past papers and just see the number of different ways that they give the information to you. Okay, mostly what they're trying to test here is your ability as a physics student to do data analysis, right? In other words, to read information off of a graph, right? Okay, all right, but in any case, in this specific one, we're talking about a group of scientists, right, which perform an experiment by shining 5 different light sources, right? So now that is very important. If I tell you that the light source is different, right, then it means that I am varying, right, the frequency, right, of the light source. Now remember that, right, so energy of a photon, okay, is dependent on the frequency of the wave. Okay, so frequency, let's just say, of the light. Okay, so which means that the minute I start playing with the frequency of the light, I'm changing the energy of that light, right? And that then affects the kinetic energy of the photoelectrons that get emitted, right? This is now contrary to what they believed before Albert Einstein actually wrote his hypothesis, which is the photoelectric effect, right? Before he wrote his hypothesis, which is now what is accepted, they used to believe, right, when the only thing we knew was something called the wave theory of light, right? We used to believe that the kinetic energy of the photoelectrons is affected by the intensity of the light. And Albert Einstein came in and showed us that no, that's not the case, right? The kinetic energy of the photoelectrons is actually affected by the frequency of the light. In other words, the energy of the light. Okay, so the energy of a photon is dependent on the frequency of the light, right? So this equation over here, energy of photon is equals to hf, or we just simply say E is equals to hf. All right, let's read on and see what else they say, right? They say that A, B, C, D, and E, right, are these different light sources, right? So these points over here on the graph are different light sources, okay, of different wavelengths, obviously, onto a platinum metal surface, okay? So that is the metal that we're using. We are shining different light sources on on a platinum metal surface. Okay. Then for each and every light source, we've measured the maximum kinetic energy, right, of the ejected photoelectrons, and the following graph has been produced. Let's just zoom into the graph a little bit and talk about it. Alright, so here's our graph, right? Remember, what did I say? I said the first thing you do is you look at the labels, right? You see, okay, on the y-axis, you've got your kinetic energy, the maximum kinetic energy, and that's talking about the kinetic energy of the photoelectron. You also need to note these things over here. These things are called units, right? So basically what you're trying to say is that if you see this number 2 over here, 2 means 2 times 10 to the negative 18 joules, right, is then the maximum kinetic energy, right? And then on the x-axis, we see frequency, right, in units of times 10 to the exponent 15 hertz. All right. Okay, so that's quite clear. Now let's do an analysis of this graph. Right. So basically what this graph is doing is that it has plotted on it different frequencies against the kinetic energy of the photoelectron, right? Now the important parts that we need to note of this graph is this section over here. First of all, we need to find the x-intercept. Can you see it over there? Okay. So we need to find the x-intercept because the x-intercepts or the x-intercept creates this division, right? We need to understand how this graph is drawn. There's this plate of metal, okay, and you then shine light on it, okay. So now let's say this is now frequency 1, okay. Now unfortunately, let's say frequency number 1 is less than the threshold frequency. Remember, when the frequency of the light is less than the threshold frequency, nothing happens, right? Right? Okay, so then you try again with another frequency number 2, and unfortunately it's still less than the threshold frequency, so then again nothing happens, right? So then this becomes this part of the graph where the frequencies are less than, let me do this, let me say the frequency of the light, okay, the incident light is less than the threshold frequency, right? Then you get this section of the graph over here, right? This section, all of these points, it's actually a horizontal line, okay? That's how the graph looks. So the graph looks like this. It's a horizontal line for some time until you get to some frequency where after that, all the frequencies beyond that create a straight line like that. Okay, so that's basically how the graph looks. Right, so for this section, all these frequencies on this side, right, including the frequency of A, right, so the frequency of this light number A is less than the threshold frequency, right, so that frequency over there, right. So including this A, point A, they had this case over here where they were not able to emit a photoelectron, okay. Now, at the x-intercept over here, right, so at the x-intercept, something special happens. At the x-intercept, you hit directly something that we call the threshold frequency, right? So at the x-intercept, you now have this case, right, where you have your metal plate, right, and then now the light that you shine on it, the frequency of this light is now special. It's now equals to the threshold frequency, right? So now what that does is that it just lifts the electrons, right, to the surface of the metal, right? So please note, no electrons are emitted yet. So no electrons emitted, but the electrons are at the surface, right? So but electrons are at the surface. Okay, so in other words, the electrons are excited, right? So now let's read off what this threshold frequency is very quickly. Let's see. So there is 1, 2, 3, 4 divisions here. So this is basically 0, and then it's 0 0.2, and then it's 0 0.4, 0 0.6, 0 0.8, and then the 1. Okay, so then after that it's going to be 1.2, sorry, then this is 1.4, but remember you always add this, so you say times 10 to the exponent 15 hertz. Right, so now that is your threshold frequency, and we found it at the x-intercept of the graph. All right, now what happens now beyond the x-intercept? Well, now the frequency of the light is greater than, okay, the threshold frequency, which is nice. So now what happens is that in this region, you're going to have the emission of photoelectrons. Okay, so in the last part, if you now emit light, okay, so frequency of light is now greater than the threshold frequency, what happens is the electron that is at the surface will then absorb, right, the energy that it needs, right, so the work function, and then the extra energy it will then use to escape from the metal, right? So it will be emitted, right? And it's going to be emitted with some maximum kinetic energy, which is what we are plotting on the y-axis. All right, so now let's answer the questions. Question 10.1 is a theory question, right? So 10.1 theory question says define, right, the work function of the metal, right? Remember this word work function has the symbol W naught. And the key words in this definition is the words minimum energy and this word surface. Okay, so these electrons are coming from the surface of the metal and not, deep inside the metal. Okay, just the ones at the surface. Okay, then we have 10.2. 10.2 then says use the information from the graph to calculate, right? Now calculate the work function of the platinum. Okay, right, so now this you need to just know basically the work function, because it's energy, right? It has to be multiplied by Planck's constant, and then you get it by multiplying the frequency is specifically the threshold frequency, which is this value here that we got from the x-intercept. Okay, so now all these values you must know. If you don't know, you can just get it from the information sheet. So we can get Planck's constant over here, right? Note the units, joules second. So 6,63 times 10 to the negative 34. Okay, so it's necessary for you to memorize them. I would, just to save me some time, but you don't need to. So it's 6,63 times 10 to the negative 34, and that's going to now be multiplied by, okay, let me not do that, that's very poor notation. Let's do this. Okay, so you're going to multiply that by the threshold frequency, which comes from the graph. So it's 1,4 times 10 to the 15. Okay, now your work function is then, okay, I just want to show you how we type this into the calculator. This is just for accuracy. You could actually use still your exponent button, which is this button, but I don't know, it just works much better and faster with these scientific numbers if you use the scientific exponent button. So you're going to say 6,63 and then you press this button. Okay, you can see that times 10 looks kind of funny, and then you simply just say negative 34 like that. Okay, and you close it. Then I'm going to add 1.4 times 10 to the exponent 15 like that. Okay, now that gives you immediately, the answer. We'll round it off to 2 decimal places, so it is 9.28. Okay, so it's 9.28 times 10 to the negative 19, and the unit for energy is joules. Okay, let's see. Question 10.3. It says, how is the number, right? The number of the ejected electrons, right? So in other words, the number of electrons that come off the surface of the metal, right? How is that affected? Okay, we're going to choose from increase, decrease, or remain the same. Okay, so 10.3.1, right? You want to know how is the number of electrons that are ejected affected if, right, the intensity of light source A is increased. Okay, so now we need to go to the graph. Okay, Back to our graph. Now remember what I said about light source number A. Because light source number A is in this region, right, with all these frequencies over here, right, all these frequencies are less than the threshold frequency of our metal, right, we say that these frequencies of light are not energetic enough, right, or strong enough, right, to even bring the electrons to the surface, right? So they do absolutely nothing to the metal, okay? So now, if the energy of that light is not strong enough, no electrons are going to be emitted, right? In other words, nothing happens, okay? So if you want to now answer this question about how is the number of electrons affected, well, it remains the same, okay? Even if you increase the intensity of that light, you can make it as bright as you want it to be, okay? What you are doing, okay? A lot of people struggle with this, so let me try and draw it. Okay, so now what is actually happening here is that you can think of this as little packets, right, in here, and these are the photons, right? Now, each of these photons have an energy associated with them, right? There's Planck's constant times the frequency of light number A, okay? Now, all of them, okay, have this energy, okay? It doesn't matter that you've changed the intensity, the energy stays the same, okay? Because the frequency stays the same. So because the frequency of A remains the same, the energy of A remains the same. Okay, so now what you are doing is when you increase the intensity, you are just hitting this metal with more of these photons that have exactly the same energy, right? You're just hitting it with more and more of the photons. You're just increasing the number of photons that you're hitting it with, but unfortunately all these photons still have H times Fa, and so long as Fa is less than the threshold frequency of this metal, that's why nothing happens. Okay, so the answer for 10.3.1 is, like I said, remains the same. Okay, so to summarize, if the frequency of the light, we call it the incident light, is less than the threshold frequency of the metal, okay, if you increase the intensity of that light, because you're just hitting the light, sorry, the metal with low energy photons. Okay, right, now let's look at 10.2.3. Right, now in 10.2.3 they say, now how are the number of electrons that are emitted affected when light source B is used instead of light source A? Okay, so let's go back to the graph. If we now use light source B, okay, here's light source number B. It's in this region where the frequency of B, okay, is going to be greater than the threshold frequency. Perfect, because it means that light source B is energetic enough to emit an electron. So light source B is in this section of our situations. Okay, so how does the number of electrons get affected? Well, it increases. Okay, basically it increases from no electrons being emitted to now some electrons being emitted. Last question. Question 10.4 says calculate the speed, right? So always remember that speed is always going to be captured in the formula for kinetic energy. Okay, that's where the speed is always going to hide itself. Right? So calculate the speed of an ejected electron when light source C, okay, is shown on the platinum plate, okay, or metal. Alright, so let's write our equation. Okay, I've already written it down. We now need to get from the graph what is the kinetic energy of the photoelectrons when we use light source C, okay, and we need the mass of the electron, which is going to come from the data sheet. Somewhere here, there it is, the mass of the electron. Okay, so what do we need about point C? We need its kinetic, or the kinetic energy of the electrons. So that's going to come from the y-axis. Okay. Now on this y-axis, the way it's going up is that this is 0.1, 0.2, 3, 4, 5, 6. This is going to be 0.7. Okay. The only thing I need to do is just multiply it by times 10 to the negative 18. Okay. Right. So in the calculator, what we're going to do, remember this is v squared. So v is going to be a square root. Okay, the opposite of that. And then basically what happened is that you divided both sides by a half, but dividing by a half is the same as multiplying by 2. So this was 2 times the 0.7 times 10 to the negative 18. Okay, so that was dividing by half, and then you're dividing by this mass, 9.11 times 10 to the negative 31. And then after that, you're taking the square root of everything. So, okay, so when this happens, we're going to change our calculator to scientific mode. So when I say mode, okay, now I'm going to say shift setup, okay, for this specific calculator. And then you're going to say number 7 for scientific. And that's going to ask you how many, what do you call them, decimal places you need. I think I need 2 decimal places. So that is now my speed. So it's 1.2 times 10 to the exponent 6. So 1.2 times 10 to the exponent 6. Look at what I did here. This is not meters per second. Wow. This is kinetic energy. So this is joules. This is the one that is meters per second. Okay. I just want to go back to the calculator and see. Usually we need 2 decimal places after the comma. So let me see if I go shift setup again, go back to scientific. This time say 3. Okay, there we go. All right. So you must type in how many digits you need. Okay, so it's 1.24. Okay. Right, so it's 1.24 times 10 to the exponent 6 meters per second. Okay,